Good morning, everyone. So today we have chaos. Well, just an introduction to chaos, and we will do it by looking at the Lorentz equations. Ed Lorentz, that was his name, in 1963 derived a very interesting system of equations. Well, what he was looking for, he was modeling weather, and he was a mathematician but interested in all these atmospheric phenomena. Well, his approach was to decrease the size of the equations dramatically, and at the end he obtained a system of equations with three variables. So it means that we have three dimensions. And his hope was that he was able to get something meaningful from these equations. So there was some parameters that he had to set up, and he realized that the equations behave very differently. For example, for a given parameter that we will recognize today as the Rayleigh number, he found that the system approached always a steady state. So imagine you have an example, imagine something very close to the Rayleigh-Bernard convection. When at the bottom you have maybe a very hot surface, at the top you have a colder surface, and you just generate some convection between the bottom and the top plates. Something recognized as convection rolls. For a very small number, Rayleigh number, the convection rolls approached the steady state and nothing moved. But when he increased the Rayleigh number, you may start having some periodicity, some unsteadiness in the flow. What he found is that after a certain Rayleigh number, there was somehow a strange situation when there were orbits. Imagine he was plotting all these three-dimensional system in a three-dimensional plot, so in a three-dimensional phase portrait, and he realized that the oscillations, they never repeated, so they were actually very different all the time. Also, he realized that any small change in the initial condition will completely change the future, or let's say the evolution of the oscillations. I think I talked about something I read in a book of the history of chaos, and something that was shocking to Lorentz was that he was, for example, working one day, and in these computers from the 1950s, 60s, and after some campaign of calculations, he stored the initial condition, and maybe the next day he restarted from the stored initial condition. But to store this initial condition, he had to somehow truncate the solution to a given few amount of decimals. Already this truncation of the initial condition was influencing that the solution will somehow evolve in a different way as if he had considered the complete solution. So this stopping and restarting of the simulations were actually producing different results all the time, and that was somehow very tricky at the beginning, because he could be thinking, okay, wait a minute, these computers, they're just coming up from to the modern world. Maybe they are not as accurate as people thought, or maybe they are failing actually. But at the end, he actually realized that it was not the computer, but it was the nature of the system he was simulating that produces this very different evolution in time, given some just initial perturbations in the initial conditions. And this is what is interesting from the system of equations of Lorentz, because this was the first time that a small amount, so a small system of equations, a three-dimensional system, ODE, was able to reproduce a very complex phenomena, maybe not very related to weather. What is important in here is that a small system of equations can produce a very complex phenomena that doesn't repeat itself. It's not just a periodic oscillation, it's something that doesn't repeat. And that's when people start getting interested in a small system of equations, and chaos theory was born. Some years later, like around the 1970s, the guys from some people from MIT reproduce a system of equations, a different system of equations that could be eventually transformed to the Lorentz equations. Something nice from this is that they were able to design a system that is actually a mechanical system, very simple in terms of design and also of modeling, that produce chaotic behavior. And this is what is called a chaotic water wheel. Okay, and this is the chaotic water wheel. So from here we can see there is some water coming from the top in a steady manner. And at the beginning, nothing is moving. You have the cups, and the cups start getting filled. And after a certain threshold, this mass flow of water make the wheel rotate to the right or to the left. Well, it depends on a given perturbation that make preferential rotation from the right than to the left. But in addition to the water that is being poured, you also have leakage on these cups. So that creates a relation between mass flow in, mass flow out, that perturbs the rotation of the water wheel. So we can see here in this video what I just said. So sometimes it rotates to the left, sometimes it rotates to the right, and this is actually happening in a chaotic manner. There is reported that people actually make bets. They wait 1 minute and they bet if they is rotating to the right or to the left, because this is actually something that you cannot predict. This is a chaotic system, and therefore if you repeat the experiment several times, you will have always a little perturbation in the initial conditions that will make the evolution of the angular velocity be different. So this is a figure representing the angular velocity of the water wheel. We saw that sometimes it rotates to the right, but the angular velocity is actually non-constant. It can oscillate, and then suddenly it can reverse the direction and go to the left, and still have a oscillatory angular velocity, and then to the right, and so on. And this signal, then if you analyze it, you can realize that it's a chaotic signal. As in the book, there is a simple formulation for the Gatter-Wheel equation. So we have the conservation of mass and the conservation of momentum. I didn't follow exactly the same procedure as in the book of Strogatz. I have some different approach, slightly different, which I consider, at least for me, is more clear. So feel free to go slowly on the slides and look at it. So the first thing is to consider a quasi one-dimensional system. So this is just, imagine a control volume from this geometry. So this control section, so this control volume we just got, we can just describe it as a one-dimensional system with an inlet and an outlet on the walls, and maybe we just put a flow direction for convention. Now let's go to this small, let's say, quick joke question. If we have this expression in here, what does it mean? The system has no mass, or the change of mass within the system is zero? Yeah, actually, the second option is the right one. This is another also silly joke, because it's a very silly question. Now what does it mean? The change of mass within the system is non-zero. The change of mass within the system is zero. Well, actually depends, no? So there is no correct or false answer. it depends on the relation of the source, the sink, and the flux that comes in, the flux that comes out. So we have here this representation of F in, F out, the source and the sink. And the flux in is just given by the mass flow in, out. And we can also express the source and the sink as integral equations along x. And here the source is going to be given by Q, and the sink is going to be given by K rho. We also consider that the velocity U is going to be constant in space. So in this control volume, we will have the velocity being constant at every single point. By using the divergence theorem, we can actually build this flux in, flux out as the divergence of rho U. And we remember this U is constant in space. Therefore, we can have something like this. And now let's remember we are actually considering this circumferential trajectory for the control volume. Therefore, it's a good idea to have polar coordinates. Okay, so do you remember we can relate x with theta? Yeah, so we can have r d theta, and then we have the velocity being equal to r times omega. And this is also a simple relation applying the chain rule. And then we can just replace this by this. So we have replaced this by this. Finally, we define then the mass, rho times r, and a quantity defining the source. So we have this expression. And after shrinking the control volume, we obtain a differential equation in terms of t and theta for the mass. And the next equation is the conservation of angular momentum. So basically is having the left hand side being equal to the damping torque plus gravitational torque. We define this capital M quantity, and the gravitational torque is just force times distance. From that relation, we can have a differential for this torque, and after integration of that differential, we can obtain the expression for the gravitational torque. The damping torque is simply considered as proportional to the angular frequency. And we recall now that this quantity here is called moment of inertia. Okay, so from this derivation we have then conservation of mass and conservation of angular momentum. The last thing is to express this quantity, which depends on the angle and time, as a superposition of harmonic signals. And the source, the inflow, is also a capital Q as a function of theta, also expressed as a Fourier series. Okay, so finally we have the equations. There are actually three in terms of three variables: A1, B1, and omega. So the one that interests ourselves the most is actually this omega. This is the angular frequency of the rotating wheel. Okay, so we have now three equations, so three ODEs. What do we do now? Yeah, we can concentrate analyzing the fixed points of that system. So basically we just need to equate these three equations, which are nonlinear, to zero to obtain the corresponding fixed points. We can see, for example, that A1, B1, omega can have these values. We can have A1, B1 like this. Again, the one that is interesting also is this omega, which is 0. That's why we call this the state of no rotation. And the question is now, is this a state of no rotation stable or unstable? Do you know? Okay, no idea yet. What do we have to do? Yeah, we have to compute the Jacobian. And there is another situation, what we call state of rotation. So A1, B1, they have a non-zero value, and omega star, so the omega at the fixed point is also non-zero. That's why we have the state of rotation. When solving or when finding the fixed points, we will see that this non-zero omega is given by the solution of this quadratic equation. And remember that we are considering the fixed points as real numbers. Therefore, omega has to be real. And in order that to happen, we have to assure that this quantity is what? Yeah, is positive. So if this quantity is positive, it means that what? So for a rotation state, we need this ratio like this. Okay, you just have to just solve this inequality. And this is very interesting because you will realize that this is just a term completely correlated with the source Q1, and this is given by the losses or the damping. So basically what this expression is telling us is that in order to have a rotation state, the sources have to be larger than the losses, which is actually intuitive. So we call these terms the driving terms, and these terms the dissipation terms. Something of interest is to give a name to this ratio, and actually this is gonna be called as right-left number. If we keep investigating the state of rotation, we would find many kind of physical behaviors. We can have periodicity, and we can have actually chaos. So something nice that can be done before keep studying these equations or this rotating wheel is to actually convert these equations, so the ones I just showed you before, to the Lorentz equations. So if we are able to make this transformation from the wheel equations to the chaotic wheel equations to the Lorentz equations, there will be a huge gain, because we could then study this rotating wheel from equations that have been already investigated a lot during the last 40 years. So we now introduce the Lorentz equations. So now the variables are x, y, z, and they are also interrelated nonlinearly. And here we have the equations we just derived, which are the water wheel equations. Okay, and now the challenge consists in transforming or expressing x in terms of y, b, omega, and so on. So we need a mapping. So in the slides, you will see that I spent like 10-15 slides more to derive step by step how we can map the water wheel variables to the variables of the Lorentz attractor. Okay, in this video we will jump this, but it's all that in the slides. So from the slides you can actually then understand how we do to arrive to these equations in here, and to relate x dot, y dot, and z dot with the variables of interest in such a way. This is actually a very nice thing, because again, as I just said before, we can start learning something about the chaotic wheel from the standard Lorentz equations. Okay, so we go back to, let's call it square one, and say, what do we do? Yeah, we want to have the fixed points first. So just remember what we obtained for the water wheel. We had a state of no rotation and a state of rotation, depending on a number that we call Rayleigh number. So if this number is larger than 1, we have this situation. Now, if we take a look at the equations of Lorentz, we have also two situations. One, when we have everything is 0, so this is like the fixed point at the origin, and we have this case in here. You will see that these fixed points, they exist only if r is larger than 1. So this is somehow related with the case of rotation for the water wheel. When Lorentz was studying these equations, he just gave a name to these fixed points. He called it C plus, C minus. Okay, this was just is r minus 1. So, as in the two-dimensional case, we just need to concentrate in one fixed point at a time, understanding what they are, so the Jacobian and the stability at each fixed point. So this is the Jacobian. So if you just from these equations obtain this, and then we replace this with the coordinates of the origin. So x, y, z, all of them being 0, which give us this result. And from this result, we already see something interesting. We see that one direction, so the z direction, is completely uncoupled from the x and y coordinates. So the x and y variables are uncoupled from z. Have also in mind that instead of having two eigendirections, now we have three eigendirections per fixed point. So let's evaluate this one first, because it's pretty simple. We have already one eigenvalue that is related by minus b. Therefore, I think this question is pretty simple for you. So which is one is the eigendirection characterizing the dynamic evolution of z, pointing towards or pointing away the origin? Yeah, is pointing towards the origin because we have a negative eigenvalue. Since the system is decoupled, as we just mentioned, we can have just the analysis of the other two directions also completely unrelated. So we can have something like this: x, y is given by minus sigma r minus 1 xz. And then we just again we compute what the trace, which is gonna be minus sigma minus 1, and we have also the determinant, so this delta, which is gonna be sigma minus sigma r, which is actually sigma 1 minus r. Now if we just remember again this, so the eigendirection is going to be tau plus minus t squared minus 4 delta over 2. So since sigma is actually positive defined, therefore tau is going to be already negative, so this is negative. And then we have to analyze also this delta. So delta is going to tell us if lambdas are from different signs or from the same sign. So if lambdas are from different sign, it means we have a saddle. Okay? And that would be possible if delta is smaller than 0. Otherwise, we will have just a stable node. If delta is larger than 0. Okay, so here, if r is smaller than 1, delta is positive and we have a stable node. So all three eigenvectors point towards the origin, and these two, so x, y, they point towards the origin as long as r is smaller than 1. Now we have to study the stability of these fixed points, C plus. And let's consider what happens for r larger than 1. So again, if we introduce the values of x, y, and z into the Jacobian, we obtain this situation. This is not as simple as before. Now the dynamics of x, y, and z, we can see here, is coupled. The next step is then to find the eigenvalues. So now we will have 3 eigenvalues, but we will have to solve a cubic equation for lambda, which is actually much more, let's say, nasty than a quadratic equation. After solving this cubic equation for lambda, we realize that actually the fixed point C plus is stable between a given range of r, from 1 to a so-called RH. And it can be shown that this is actually a Hopf bifurcation given by these quantities. So let's do a summary. For r smaller than 1, we know that the origin is a stable node, so it's an attractor. And therefore we just draw here in this bifurcation plot the x equal to 0. Then in here, then we have that the origin becomes a saddle in xy, and therefore it loses stability. But at the same moment, we have the appearance of two new fixed points that exist, and we have that these fixed points are actually stable between r equal to 1 and RH. We can see here that this is a clear pitchfork bifurcation. Now the question becomes, what happens for values of r larger than RH? So this has been a lot of investigation on this question for the last decades. So actually the calculations are pretty involved, but we can just show, for example, what is the situation, what is actually happening. We can learn from those studies. We actually see that the fixed point, therefore, becomes unstable, and something else happens, is that now we have here a Hopf bifurcation, which is actually subcritical, if you can see in here, the direction of the unstable limit cycle. Now I want that we concentrate in this question. What happens if an initial condition is established for r larger than RH? So this is our bifurcation plot. We have a fixed value of r, therefore this dot could eventually move for a given value of r. So what happens? So I give you several possibilities. This point goes to infinity, so it just goes away. Or it does not move, it stays frozen there. Or it does not go to infinity. Okay, but for that one we will need like another fixed point, no? Or it moves without stopping, maybe something like this. Hmm? And yeah, actually, okay, this one maybe is not obvious because you could say, yeah, we have here a given repeller, so eventually we can just go to infinity. So this is not obvious. This one actually is wrong because if it doesn't move, it will have to be a fixed point. It does not go to infinity. Okay, fine, but this is actually not obvious at all, and it moves without stopping, which is also not obvious at all. So it's gonna be moving like this forever. So we can say that oscillations are therefore chaotic. In that sense, we can have this situation that we are moving. Okay, if you go back and see what is actually x, you will see that this is directly related to omega when we have this transformation from the water-wheel equations to the Lorentz equations. Therefore, we can think of x as omega, and then we can think that this is actually, we have a given Rayleigh coefficient. So imagine we have a given amount of water dropping in, and maybe we have a certain level of leakage, but again the sources are stronger than the losses, in such a way that the Rayleigh number is around this value, and in that sense we will have the omega that will change. So we will be maybe rotating to the right, is going to be positive, and suddenly it's going to move in here and it's going to be negative, but it's still the omega is going to be moving without stopping. Remember that x is related to omega, and we will have this behavior changing like this forever. So we see something similar in here if we consider the y direction. There's going to be negative, positive, negative, positive, and this resembles, if you go back to the first slides, when the angular frequency of the chaotic wheel was being plotted against time. But a very nice thing happens if we plot this signal in the phase space, in the three-dimensional phase space. And we obtain this shape. This is the famous butterfly. Okay, this is somehow silly but also important to clarify, is that you can say, wait, but you have trajectories that are actually intersecting. How is it possible if we are looking at a phase space? So we just have to remember that we are just looking at the three-dimensional phase space. So of course, if you just make the rotation, you will see that these trajectories, they do not intersect. Something else that we can actually realize now, so to see how this bifurcation plot is related to this. So right now, if we are talking about chaos, then we have to be talking about a Rayleigh number that is higher than the Rayleigh number of the Hopf bifurcation. So somewhere in here, so we can actually still consider our point, our dot, okay? And this has x, y, z axis. And also remember that we have given name to these fixed points. This is called C plus and this is called C minus. Okay, so these C plus, C minus, they actually are unstable after RH. Okay, so that's why our dot is gonna oscillate somehow around them, and then we'll just switch to the other one and then switch to the other one. So basically it's just turning in here, and so on. So this is how you can actually relate the bifurcation plot to the three-dimensional butterfly strange attractor. So we have here the strange attractor of Lorentz. One of the most important properties of chaos is that solutions are strongly dependent on initial conditions. And this is a way of portraying this dependence. So imagine, so you can state this phase plane, and you can just put any point in this object, and then you just let it evolve, because this is this face portrait. Okay, so every single point when you put your initial dot is gonna be the initial condition. Now imagine you put two dots that are super close to each other, so that means this little thing in here. So basically you expect, so in a normal system that is deterministic but not chaotic, you will expect that these two dots, they are, imagine you are very close friends, that they just remain together for a long time, even forever, when just orbiting. But this is for a deterministic case without chaotic characteristics. For chaotic cases, like this butterfly effect, this is what happens. You have these two dots that are very close, and there are some period of time where they remain close, but suddenly they start deviating each other. So this is something we can see here. There is a lot of different initial conditions already like collected in this little dot in here, and then you just let time evolve. You will see how the little dots start deviating from each other, but still they are like localized in the same region. But after a certain time they start just being placed everywhere in the stretch attractor, and eventually after a certain time you will have that there are dots everywhere in this butterfly object. So do you remember this example? This is the one we discussed in the first lecture when we were talking about chaos. So actually a two pendulum system can also exhibit chaos, and you will see that at the beginning the evolution is very similar, and then after a certain time horizon the behavior of the pendulums will completely change. So let's wait for the next one. So just be concentrated when at the initial part. So you will see here is very close. You see, it's very similar what they are doing, but suddenly they start deviating. Okay, saying suddenly maybe it's not too precise, because we will show just in the next slides that there is something called the distance between two initial conditions, and they evolve. So this distance evolve exponentially, and this distance is related to the Lyapunov exponent. And what are the practical implications of this dependence on initial conditions? Well, basically the long-term predictions are impossible in a chaotic system. So we need to be God to be able to do that. What I meant is that you need to know, or to be able to have the complete control of your initial condition if you want to predict what is going to happen. But in the real world, it's impossible to have a exactly well defined initial condition, even in a numerical simulation. Because in a numerical simulation, you just have a given accuracy given by the number of decimals you impose in the initial condition. Even a double precision floating point format doesn't make it. That is actually why predicting weather is super hard. And let's introduce then the Lyapunov exponent. We have the distance between two trajectories is going to be given by this delta, and then we will see that this is actually evolving exponentially. So you have here a given initial distance, and this initial distance will deviate. So if we reorganize this equation, so we just need to multiply a natural logarithm to the left and to the right, we will be able to have an expression for lambda, for the Lyapunov exponent, or for the time horizon. It depends on what you want. So given a value for the Lyapunov exponent, we can assure that after a certain time horizon, the distance is not larger than a predetermined tolerance. So rearranging the previous equation, then we will have this equation for the time horizon depending on the tolerance A and of the Lyapunov exponent, and also on the initial distance between two initial conditions. This is a very nice example given by Strogatz. It refers to how time horizon is influenced by the initial value of this delta naught. Imagine you're in a company that is responsible to describe, to predict weather, okay? And you have a given machinery, some measurements instruments that are devoted to measure, for example, pressure, temperature at a given locations within a region. And you know that the tolerance of those elements is limited. So let's assume you have a certain tolerance which is given by 10 to the minus 7, okay? So you know that you are somehow missing the truth, at least by this factor. Additionally, you decide that this is the tolerance of your predictions, okay? See, it cannot be larger than this 10 to the minus 3. This is what you suppose. So based on that, you can actually already know that the time horizon depends on the Lyapunov exponent like this. Clearly here, the larger the Lyapunov exponent, the less amount of time you are able to predict within this accuracy. So suddenly you realize, or you are given the task of increase the time horizon, this time window, where your prediction is actually accurate, so below this tolerance. And someone gives you the idea of buying new tools so that you can actually measure with a high precision. So you invest a lot of money to be able to decrease by 1,000,000 the error given by your measurement instruments. Well, and then you just realize the same calculation and you realize that you have increased the time horizon. Magnific, okay? But now you say how much have actually increased this time horizon. And you realize that you have increased it by just a factor of 2.5. So the question is it worth to invest all this amount of money so that the accuracy of the instruments increase by 1,000,000? Yet the time horizon you actually predict is just 2.5 times larger. Well, I think this is actually very bad news for weather forecast, isn't it? You can put all the money and the motivation in increasing the time horizon, so to go from 3 to 4 days of precision in the time weather forecast. Still, the investment would be huge, but the effect wouldn't be much. So, ladies and gentlemen, this is chaos. So now that we have learned some properties of chaos, we would like to model it. So the Lorentz attractor is one, for example, but there are also other kind of attractors which are actually called strange attractors. And mathematicians has actually found out a way of modeling them in a very smart and simple way. So basically, the idea is you will have like a dough. So imagine you're doing breath, just to understand what is this about, okay? And this is just composed by a collection of initial conditions. So they are all together at a given point. And then you just start doing some flattening and stretching and folding, and then you just put it back. So to understand what I'm talking about, let's just watch a video. So imagine you have just a collection of initial conditions. Every single sphere, these yellow and white ones, are in a three-dimensional space and are placed at a given position. So it's a given initial condition. Then what does an stretch attractor do?
After a while, they all accumulate on the same butterfly.
This is a nice video. You can just look for chaos in YouTube and you will find this kind of videos which are actually pretty illustrative and interesting. So that's that. So you have this initial dough, and imagine you put just three little seeds of a given ingredient. I don't cook, so I don't bake, sorry. But okay, we have these three seeds that are very close to each other, and then we just do this flatten folding reinjection. So going back again to the, and you will see that after some iterations you will have these three seeds not being together, they are just separated. Still they are confined within a given region, so which is actually the dough. Here is how can you depict this stretching and folding like several times. You can go from here to here, then to here. And based on this, we can actually already identify some properties. So the first property is this example with the seeds. So we will have a process that has extremely high sensitive to initial conditions. So you can just have two seeds that are very close, and after a certain time one is going to be here and one is going to be there, so they are far away. However, they are still confined within a bounded region, which is given by this the space occupied by the dough. Another very interesting property is this fractal structure. After a stretching and folding n times, you will start to find like patterns that repeat once you zoom in. So we can give other examples if we look at other strange attractors. So this is the face space, and you just make zoom and you realize you have three lines or three lines. Now this blue square is here, this one, and now you find these three lines, but this line has also three lines, so we'll do the zoom, and finally we obtain this. So this pattern is basically the same as this one, and now we'll have the same pattern here. So this fractality is basically clear in this example. So this is a way of you can identify a strange attractor. Okay, so let's aim at defining chaos and the strange attractor. Chaos is a periodic long-term behavior in a deterministic system, that exhibits sensitive dependence on initial conditions. So when we talk about a periodic long-term behavior, it means that we have no fixed points, we have no periodic orbits, we have no quasi-periodic orbits as time goes to infinity. So you cannot actually see any of this happening. Once you start increasing the time window, you don't find any pattern. So this is what aperiodic means. Deterministic system, so this is something we already know, is so given an initial condition, we can have here, let's call it U, and this is our deterministic system, and then we will get Y. Anyway, we know U, so we have complete control of U. Given that fact, we know what is going to happen with Y. This is something we can do. Okay, now if you have a random system, you could have the same U and you give a one I, but then you repeat the same process and you will a different Y, because you have somehow a noisy system that is not deterministic. Okay, so let me just, so let's have this example in here. We have the deterministic case, and we inject 2 times U1, and then we obtain Y1, Y1. So it's deterministic, so nothing changes. If we had a stochastic system, we inject U1, we obtain Y1, let's say, but then if we repeat the process, we get V1 and then we get Y2. So actually, the fact of this system being stochastic doesn't assure that we will have the same mapping. But all this happens in the ideal world. The problem is that we live in the real world, and in the real world it's impossible to impose u1 this the first time and the second time. How we know that we're imposing exactly the same u1? It's very difficult to do that. So that's why it's very easy to confound or to misinterpret chaos by randomness. Okay, because in the real world you think you are introducing the same u and you obtain different y's, and you say, yeah, actually it's because the system is stochastic, but maybe it's because you were not able to impose exactly the same initial condition, the same initial input. Okay, so this is something to take into account. But since we are now defining chaos, we have to keep this in mind. Chaos is deterministic, and this is something that we were just explaining the example also. So chaos is highly sensitive to initial conditions. So nearby trajectories separate exponentially fast. Exponentially, you can already think about this Lyapunov exponent. Okay, now, what is an attractor? An attractor is a set to which all neighboring trajectories converge, and the strange attractor exhibits sensitive dependence to initial conditions, and they are usually fractal sets. This is what we just shown in the previous slide. We also see that a model for a strange attractor is given by this making path tree perspective, by making some stretching and folding. So that's actually what a strange attractor does. Okay, and now let's talk a bit about this Lorentz map. And the most interesting concept in here is that you can actually obtain order from chaos, and this is something that is maybe not everyone knows. So analyzing chaos or a chaotic signal is sometimes not straightforward, and there are many techniques to do that. That seems to be like driven from empiric like ideas. So one idea of Lorentz was to plot the value of the peaks. So he just denotes, for example, a given peak being n, another being n plus 1, n plus 2, n plus 3, and just have an axis that is present, and this is the future peak. So this is shown in this map. Okay, so these dots are a collection, let's say, of peaks that he just tracked from this signal, from a very large signal. And you will see that maybe contrary to the expectation, maybe you could expect something that is just completely going everywhere. He just found that it just followed like a very clear line. So just to be sure that we understand, this is not just plotting one point after the other like this. It doesn't work like this. You just plot it from a given amount of time. So you can start the first peak in here, then you measure the second peak and the second relation, then maybe it's here, then the other is here, the other is here, and after a collection of many collection of data of a long time series, then you just get this kind of case. So you may think this is basically also one-dimensional, which is very interesting. So if you look and you do a zoom, you will see that actually this is not exactly a line, but the nice thing is it can be represented by a line. So the nice thing is that you actually can have order from chaos. And this is at some point a fractal. You can find also patterns of fractality in this Lorentz map, and we can actually extrapolate this concept of order from chaos if we look at more like popular fractals, as the ones I show in the first class, when you can see really two-dimensional maps in the complex plane, and you see these very disorganized patterns. So just go and look in Google if you want fractals, and you will see that they are actually even revealing some natural structures like a leaf, for example. This is also related to the live game or the cellular automata I showed in the first lecture. So all these order from chaos. Okay, so let's walk through the jungle. Now let's see the big picture. So this is what we have seen today. We have seen an origin being stable, three fixed points showing up. So we have a pitchfork bifurcation. We have the origin becoming unstable, and then we have these two stable fixed points that also have or they have a half bifurcation. Then you have here some unstable limit cycles, and these fixed points become unstable. So this is what we have seen so far, and we have identified that chaos is somehow happening in this region. But this kind of system has been studied a lot during the past decades. And you can just see, for example, if we do a zoom of this half part of the bifurcation plot, we can see something like this. So every single number here is, for example, a long chain of studies you can find in papers. So this actually is very involved. So the methods used to obtain this kind of numbers. Okay. So for example, this is what we already know. So we know that the half point is at 24.74, the live number, and we will have here an strange attractor. So this is chaos. We can also have this region when you have actually the fixed points. So if you happen to be close to the fixed to this trajectory, so you will get attracted to the fixed points. But if you are far away, so you are in here, for example, you will be actually just having some chaotic behavior. But if you happen to cross the line, then you will get attracted to the fixed point. So you will have a period of a time window when you actually exhibit chaos, but then you just go to a stable state. So this is what is called transient chaos. Okay, and also these numbers are well identified. So this is to show you that the Lorentz attractor has been largely studied. And as the Lorentz attractor, there are also many other attractors that can be studied in the same way, so similarly. So identified, like with a bifurcation plot, what is happening with the system. And now this slide, the end. So I put it on purpose in here because this is a little bit like abrupt. You say, oh, now everything is finished, this is the end. But I want just to point out that this is not the end, this is just the starting. You will see that this was a very quick introduction, brief introduction of chaos. You get somehow the flavor of what it is, but there's a huge field of study, so you can just immerse in there. And as I also suggested, you can actually go look for more mathematical driven courses on chaos that are offered at the mathematical department at TUM, for example by Christian Kuhn. And as a final part, before just saying goodbye, although I have to remind you that next class is going to be an overview of thermoacoustics and nonlinear dynamics. So this is also interesting for you if you want to do a master thesis, heavy or something like that. It would be nice, so that you are getting involved in the topics of the department. Well, I would feel guilty if I don't introduce to you this equation, which is somehow referred to a logistic map. So I find this just fun, so please explore this equation. Now you can see that we are talking about discrete time instead of continuous time. Okay, and you will see that given different values of r, this equation behaves completely different, and this simple equation can actually exhibit chaos. And this is actually until now the smallest system that people know that actually exhibit this kind of complexity in itself. So you find this in the page 353 of the book. I will just also invite you to look at this video, YouTube, and you can see the logistic map and how rich it is, and also how impressive is this fractal behavior that this equation gives. Okay, you can find this kind of videos in YouTube. You just type logistic map.
We're going to explore the structure of the logistic map orbit diagram just a little bit more. This is a screenshot of a Java applet. And so we have our familiar single fixed point, and then at r equals 3, we have the bifurcation where it becomes unstable, not shown on this orbit diagram, and a period 2 orbit that's stable is born, and then we have another period doubling and another period doubling. And what we can do with this applet is zoom in on a small little piece of this orbit diagram and see that when we zoom in, we're seeing a copy that looks a lot like the whole thing. So on this zoomed in version, note that we have a small range of R right now. We can still see this period 3 window, and we can also see other little miniature copies if we zoom in again. So I just zoomed in, my range got smaller. I can see another period 3 window and another piece here where I can zoom in. I get that period 3 window again and all these pieces. I'm going to zoom in a slightly different place in the diagram right now, in the middle of the period 3 window. Okay, still seeing copies of this fig tree. Branch, and that period 3 window. Gonna zoom in right here. Okay, we have the same thing, distorted and bent a little, but very similar to the overall diagram. Maybe I'm gonna go down here now. Okay, and
Okay, so you can see that it can be like this like forever. So this is actually very interesting to see that this small equation can produce this kind of rich results. Okay, so just keep it in mind. Well guys, so that's all for the class, for the content in the class. I hope you have enjoyed, and again we see you next week to talk about nonlinear dynamics in thermoacoustics and also a little bit of chaos. Okay, so bye bye.